Far beyond Neptune, in the dark outer reaches of our solar system, something may be hiding. For years, astronomers have noticed strange patterns in the orbits of distant icy worlds. The evidence is incomplete, the mystery remains unsolved, and yet one possibility continues to stand out: a giant hidden planet that no telescope has seen directly. Tonight we follow the clues leading to one of the most intriguing discoveries in modern astronomy. If this world truly exists, it could reshape our understanding of how the solar system formed, evolved, and survived for billions of years. Before we begin, take a moment to like this video and subscribe to Cosmic Bedtime Stories. Every like and subscription helps the channel continue exploring the universe's greatest mysteries. Now, as the known planets fade into the distance and the sun becomes just another bright star, the search begins for a world that may be changing everything from the shadows. At the farthest reach of the sun's influence, space gradually shifts from a region dominated by solar particles into a more balanced environment shaped by the broader galaxy. This distant boundary is not a sharp wall, but a slow transition where conditions change over vast distances. The sun continuously emits a stream of charged particles known as the solar wind, a thin but persistent flow that expands outward in all directions. As this flow travels farther from the sun, it carries the structure of the inner solar system into deep space, gradually weakening as it encounters material from the interstellar medium, the diffuse gas and dust that fills the space between stars. The outermost influence of the solar wind forms a vast bubble known as the heliosphere. This structure extends far beyond the orbits of the known planets, enveloping all major planetary regions and continuing outward until it interacts with interstellar space. Within this bubble, the solar wind maintains a dominant role in shaping particle behavior. The density of solar particles decreases with distance, and their energy distribution changes as they expand into a larger volume. Magnetic fields carried by the solar wind stretch outward as well, forming a spiraling structure that reflects the rotation of the sun. This structure remains coherent across enormous distances even as its strength diminishes. At the outer edge of the heliosphere, the solar wind slows significantly. This region is known as the termination shock, where the outward flow of solar particles begins to lose speed due to interaction with the surrounding interstellar medium. The slowdown occurs because the pressure from interstellar gas gradually balances the outward pressure of the solar wind. In this region, particles are compressed and heated, changing their behavior in measurable ways. Spacecraft that have traveled through this region detect shifts in particle density and magnetic field orientation, providing direct evidence of the transition. Beyond the termination shock lies a broader, more turbulent zone called the heliosheath. Here the solar wind no longer flows smoothly outward, but becomes irregular and compressed. The energy carried by solar particles is redistributed through interactions with interstellar material, creating a region of complex plasma behavior. The heliosheath is not uniform. It contains fluctuations in density and magnetic intensity that reflect the constant interaction between solar influence and galactic environment. Despite its distance from the sun, this region still carries traces of solar origin, but they are increasingly diluted. At the outer boundary of the heliosheath lies the heliopause, the point where solar influence effectively gives way to interstellar space. This boundary is defined not by solid matter, but by a balance of pressure between outward solar wind and incoming interstellar particles. On one side of the heliopause, the environment is shaped primarily by the sun. On the other side, it is shaped by the galaxy itself. The transition is not perfectly smooth, and variations in magnetic fields and particle densities create a shifting interface that changes over time. Beyond this boundary, interstellar space begins in earnest. The environment here is filled with extremely low-density gas, primarily hydrogen and helium, left over from earlier generations of stars. This material is spread across vast distances, forming a faint but persistent medium through which the solar system moves. The local interstellar cloud surrounding the solar system is not uniform, containing variations in temperature, density, and magnetic structure. These variations influence how the heliosphere itself is shaped, causing asymmetries in its boundary. The motion of the solar system through this interstellar environment is slow on human timescales, but significant on astronomical scales. As the Sun travels through the galaxy, it carries its heliosphere along with it, constantly reshaping the boundary where solar and interstellar forces meet. This motion influences the structure of the heliosphere, compressing it in some directions, while allowing it to extend further in others. The resulting shape is not spherical, but elongated and dynamic, responding continuously to external conditions. In this outer region, charged particles from distant cosmic sources also begin to play a more noticeable role. Cosmic rays, high-energy particles originating from supernovae and other energetic events, penetrate the heliosphere from interstellar space. The heliosphere acts as a partial shield, reducing the intensity of these particles within its boundaries. As distance from the Sun increases, this shielding effect weakens, allowing more cosmic radiation to enter. The balance between solar shielding and interstellar radiation defines much of the physical character of this distant zone. Space in this region is not empty, but it is extremely diffuse. Atoms are separated by vast distances and collisions between particles are rare. Even so, over long periods, these sparse interactions contribute to the slow evolution of the interstellar environment. Magnetic fields threading through this space influence particle motion, guiding charged particles along invisible lines that stretch across light years. These fields are weak compared to those near stars, but they are persistent and widespread. The outer solar boundary region therefore represents a gradual transition rather than a distinct edge. It is a place where solar influence fades and galactic conditions emerge, blending into one another across enormous distances. The physics of this region is governed by balance and interaction, rather than dominance of a single force. Solar particles, interstellar gas, and cosmic radiation all coexist in varying proportions, creating a layered structure that reflects both local and galactic processes. This distant environment also serves as a record of motion through the galaxy. As the heliosphere responds to changing interstellar conditions, it preserves information about the surrounding medium. Variations in density and magnetic fields can reveal the structure of the space through which the solar system travels. Over long timescales, these interactions contribute to a dynamic boundary that evolves as both solar output and galactic environment change. Within this outermost region, the concept of distance from the Sun becomes less about planetary orbits and more about interaction zones. The influence of the Sun is still present, but it is no longer dominant. Instead, it becomes one factor among many shaping the environment. This gradual shift marks the beginning of the broader outer solar system context, where gravitational and material influences begin to diversify and expand beyond the immediate solar boundary. Beyond the fading edge of the Sun's immediate influence, the structure of the outer solar system becomes more clearly defined by a wide, flattened distribution of icy bodies known as the Kuiper Belt. This region extends roughly from the orbit of Neptune outward, for billions of kilometers, forming a broad disk-like structure around the Sun. It is not a dense band, but a sparsely populated zone, where countless small objects orbit in cold, distant paths. These bodies are remnants from the early solar system, preserving material that never fully formed into planets. The Kuiper Belt exists in a state shaped by both temperature and distance. Far from the Sun, solar radiation is weak, and surface temperatures remain extremely low, often only a few tens of degrees above absolute zero. In this environment, volatile compounds such as water, methane, and ammonia exist in frozen form coating the surfaces of icy objects. These materials give Kuiper belt bodies their reflective and often pale appearance when observed through telescopes, though most remain too small and distant to be seen in detail. The distribution of objects within this belt is not uniform. Instead, it reflects a history of gravitational interactions and gradual reshaping by the giant planets, especially Neptune. During the early formation of the solar system, planetary migration likely influenced how material was scattered outward. As a result, the Kuiper belt contains both relatively stable populations and dynamically disturbed objects. This mixture provides important clues about how the outer solar system evolved over time. Within the broad structure of the belt, countless small icy bodies follow independent orbits around the Sun. These orbits vary in shape, ranging from nearly circular paths to more elongated trajectories. The gravitational pull of the Sun remains the dominant force, but its influence weakens with distance, allowing other gravitational interactions to play a more noticeable role. Over long periods, even small perturbations can shift the paths of these distant objects. The material composition of Kuiper belt objects reflects their origin in the early protoplanetary disk. This disk was a rotating cloud of gas and dust surrounding the young Sun, where particles gradually collided and clumped together. In the inner regions, higher temperatures led to the formation of rocky planets, while in the outer regions, colder conditions allowed ice-rich bodies to remain stable. The Kuiper belt preserves this outer reservoir of primordial material largely unchanged compared to inner solar system bodies that experience stronger heating and geological activity. Some objects in this region are relatively large, reaching sizes comparable to dwarf planets. These larger bodies can maintain more complex internal structures, including layered compositions where rock and ice are separated by density. In certain cases, weak internal heating from radioactive decay may produce limited geological activity beneath their frozen surfaces. However, most Kuiper belt objects remain geologically quiet, with surfaces shaped primarily by impacts and radiation exposure over billions of years. The orbital distribution of these objects provides insight into the gravitational architecture of the outer solar system. Many bodies exist in stable zones where their orbits remain relatively unchanged over long timescales. These stable regions are influenced by resonances with Neptune, where orbital periods align in simple ratios with the planet's motion. Such resonances help maintain the structure of the belt and prevent widespread scattering of material. Between these stable populations lie regions where orbits are less regular. In these areas, gravitational influences can gradually alter trajectories, leading to slow diffusion of objects into different parts of the outer solar system. This ongoing process reflects the dynamic nature of the Kuiper belt, which is not a static structure, but a slowly evolving one shaped by continuous gravitational interactions. The density of material in the Kuiper belt is extremely low compared to the inner solar system. Even though it contains vast numbers of objects, the distances between them are enormous. Spacecraft passing through this region would encounter very few particles or bodies. The belt's vastness makes it difficult to observe comprehensively, and much of its population remains undetected due to the faintness of distant objects. Observations of reflected sunlight from Kuiper belt objects reveal important information about their surfaces. Variations in brightness and color suggest differences in composition, with some objects appearing more reddish due to radiation-processed organic compounds, while others retain more neutral or icy tones. These differences reflect both the original composition of the solar nebula and the long-term effects of space weathering. The Kuiper belt also serves as a source region for certain types of comets. When gravitational interactions disturb the orbits of icy bodies, some are sent inward toward the Sun. As they approach warmer regions of the solar system, their frozen materials begin to sublimate, forming visible coma and tails. These comets provide a temporary glimpse into the composition of the distant outer solar system. The structure of the Kuiper belt is therefore both a remnant and an active system. It preserves ancient material while also serving as a reservoir for dynamically evolving objects. Its wide distribution reflects billions of years of gravitational shaping, yet its basic composition remains largely unchanged since the early solar system. This combination of stability and gradual change defines its role in the outer solar system. As a whole, the Kuiper belt forms the first major structured region beyond the planets, marking a transition from planetary dominance to a more diffuse and primordial environment. It represents a boundary where the solar system begins to blend into the broader population of small bodies that extend outward into deeper space. Within the broader Kuiper belt, a distinct population of objects follows relatively stable and predictable orbits that remain only weakly disturbed over billions of years. These bodies are known as classical Kuiper belt objects, and they occupy a region where gravitational conditions allow long-term orbital stability. Their motion around the Sun is primarily governed by solar gravity, with only minor perturbations from Neptune and other distant influences. This stability makes them important traces of the original structure of the outer solar system. The classical population tends to reside between strong orbital resonances with Neptune. In these regions, the gravitational effects of Neptune do not strongly disrupt their paths, allowing their orbits to remain relatively smooth and consistent. As a result, these objects preserve orbital characteristics that may closely resemble conditions from the early solar system. Their study provides insight into how material was distributed during the formation phase of the planetary system. The orbits of classical Kuiper belt objects are typically close to circular, though not perfectly so. Their orbital eccentricities remain low, meaning their distance from the Sun does not vary dramatically over a single orbit. This contrasts with more dynamically disturbed populations found farther out or in resonant regions. The relatively gentle nature of these orbits suggests a long history of gradual evolution rather than violent scattering. Inclination, or the tilt of an orbit relative to the general plane of the solar system, varies within the classical population. Some objects remain close to the central plane where most planets orbit, while others are tilted at moderate angles. This range of inclinations indicates that the early Kuiper belt was not entirely flat, but experienced processes that introduced vertical dispersion over time. These processes may include weak gravitational interactions and early dynamical heating during planetary migration. The composition of classical Kuiper belt objects reflects their origin in the cold outer regions of the protoplanetary disk. They are primarily composed of frozen volatiles, such as water ice, methane ice, and nitrogen compounds mixed with rocky material. This mixture suggests that they formed in an environment where low temperatures allowed volatile substances to condense and remain stable. Over time, these materials have been exposed to radiation and micrometeorite impact, gradually altering their surfaces. Surface properties of these objects vary depending on their size, composition, and exposure history. Some display relatively bright surfaces due to fresh ice, while others appear darker as a result of space weathering. The darkening process occurs when cosmic radiation breaks down surface molecules, forming complex organic compounds that absorb more sunlight. This gradual transformation affects how these objects reflect light and how they are observed from Earth. Despite their stability, classical Kuiper belt objects are not entirely isolated from gravitational influences. Over long time scales, weak interactions with Neptune and other distant forces can slowly modify their orbits. These changes occur gradually over millions or billions of years and do not significantly disrupt the overall structure of the classical population. Instead, they contribute to a slow and continuous evolution of orbital characteristics. The distribution of these objects provides clues about the early migration of the giant planets. Models of solar system formation suggest that Neptune may have moved outward after its initial formation, reshaping the distribution of small bodies in the outer solar system. The presence and structure of the classical Kuiper belt support the idea that this migration was not chaotic enough to completely disrupt all stable orbits, allowing a population of objects to remain relatively undisturbed. The classical region also serves as a reference point for distinguishing more dynamically complex populations. By comparing classical objects with resonant and scattered populations, astronomers can identify the effects of gravitational perturbations over time. This comparative approach helps reconstruct the history of orbital evolution in the outer solar system, revealing patterns that are not immediately visible from current configurations alone. In terms of scale, classical Kuiper belt objects are typically small, compared to planets ranging from minor icy bodies to larger dwarf planet candidates. Even the largest among them remain far below planetary size, lacking sufficient mass to clear their orbital zones or dominate their surroundings. Their gravitational influence is minimal on a system-wide scale, yet collectively they form an important structural component of the outer solar system. The environment in which these objects exist is extremely sparse. Collisions between classical Kuiper belt objects are rare due to the vast distances separating them. As a result, their surfaces preserve long histories of exposure without frequent large-scale disruption. This makes them valuable records of early solar system conditions, effectively acting as time capsules of primordial material. The classical Kuiper belt therefore represents a region of relative order within the broader outer solar system. Its objects follow stable, gently varying paths that reflect both the initial conditions of formation and the long-term influence of distant gravitational forces. While not completely unchanged, this region evolves slowly enough to preserve much of its original structure, offering a window into the early architecture of the solar system. As this population is studied in greater detail, it continues to provide constraints on models of planetary formation and migration. The balance between stability and subtle change within the classical Kuiper belt remains a key factor in understanding how the outer solar system developed into its present form. Beyond the classical population of the Kuiper belt, a different structural pattern emerges where orbital motion is strongly shaped by resonance with Neptune. In this region, objects do not simply follow independent paths around the Sun, but instead move in rhythmic coordination with the gravitational influence of the distant giant planet. This resonance occurs when the orbital period of a smaller body forms a simple numerical ratio with Neptune's orbital period, creating repeating gravitational interactions that stabilize or reshape the orbit over long timescales. These resonant objects occupy regions where Neptune's gravity does not simply disturb motion, but instead organizes it into repeating cycles. Each time a resonant object completes a certain number of orbits, Neptune completes a corresponding number of its own, and the gravitational alignment repeats in a predictable pattern. This repetition prevents close encounters between the object and Neptune, even when their paths cross similar radial distances from the Sun. The result is a form of orbital protection where resonance acts as a stabilizing mechanism rather than a disruptive one. The most widely studied resonant population includes objects in a 3-to-2 resonance with Neptune, meaning they complete 3 orbits around the Sun for every 2 orbits of Neptune. This configuration creates a repeating gravitational rhythm that maintains long-term orbital stability. Within this resonance, objects can have moderately elongated orbits, but their timing ensures that they avoid direct close approaches to Neptune. This balance between shape and timing is a key feature of resonant dynamics in the outer solar system. Other resonant ratios exist as well, forming a layered structure of orbital niches. Some objects follow higher-order resonances, where the numerical relationships between orbital periods are more complex. Even in these cases, the underlying principle remains the same. Periodic gravitational influence creates a stable repeating pattern that constrains motion over long periods. These resonances act as invisible scaffolding within the Kuiper belt, shaping where objects can persist over billions of years. The formation of resonant populations is closely tied to the early movement of Neptune during the solar system's evolution. As Neptune migrated outward, its gravitational influence swept through the surrounding disk of icy material. During this process, some objects were captured into resonant motion, locking into stable orbital relationships as the planet moved. This mechanism explains why resonant populations are abundant in certain regions and sparse in others, reflecting a dynamic history of planetary migration rather than a static arrangement. Once captured into resonance, objects can remain there for extremely long periods. The stability of these orbits depends on the persistence of the resonance condition, which continues as long as the orbital relationship with Neptune is maintained. Small variations in orbital shape or inclination can occur, but the overall resonant structure remains intact. This long-term stability allows resonant objects to preserve information about past dynamical processes in the outer solar system. The orbital shapes of resonant Kuiper belt objects often differ from those in the classical region. Many exhibit more elongated orbits with greater variation in distance from the Sun over a single orbital cycle. Despite this variation, the timing of their motion remains tightly controlled by resonance. This combination of geometric flexibility and temporal constraint is a defining characteristic of resonant populations. Inclinations within resonant populations can also vary significantly. Some objects remain close to the main plane of the solar system, while others are tilted at substantial angles. These variations suggest that resonance does not strictly constrain orbital tilt, but instead governs the timing and radial structure of motion. Over long timescales, gravitational interactions within the resonant framework can still lead to gradual changes in orbital inclination. Surface properties of resonant objects are influenced by both their composition and their dynamical history. Many share similar icy compositions with other Kuiper belt bodies, including frozen water, methane, and nitrogen compounds. However, their exposure to varying solar distances over elongated orbits can lead to different patterns of surface processing. Regions of their surfaces may experience alternating periods of radiation exposure and relative shielding, producing complex and varied surface textures. The distribution of resonant objects provides strong evidence for the role of planetary migration in shaping the outer solar system. Without Neptune's outward movement, it is unlikely that such a structured resonant population would exist in its current form. The presence of these objects supports models in which the outer solar system was not formed in its present configuration, but evolved through gradual reorganization, driven by gravitational interactions among the giant planets and surrounding small bodies. Resonant motion also plays a role in protecting certain objects from long-term destabilization. Without resonance, many of these bodies would eventually experience close encounters with Neptune that could alter or eject them from their current orbits. The resonance structure prevents this outcome by maintaining synchronized timing, ensuring that encounters occur only when relative positions are not disruptive. This mechanism allows resonant objects to persist in regions that might otherwise be dynamically unstable. The study of resonant Kuiper belt objects also provides insight into the broader mechanics of orbital dynamics. Resonance is not limited to simple two-body interactions, but can involve complex gravitational relationships that emerge naturally in multi-body systems. In the outer solar system, these interactions create a layered structure where stability arises from repetition rather than isolation. Despite their stability, resonant populations are not completely static. Over extremely long timescales, subtle gravitational influences from other planets and passing stars can gradually alter resonance conditions. Some objects may slowly drift between resonant states or transition into non-resonant orbits. However, these processes occur over timescales far longer than human observation, making resonant populations appear stable within current observational windows. The resonant structure of the Kuiper belt therefore represents a dynamic balance between motion and constraint. It reflects a history of planetary migration, gravitational capture, and long-term orbital maintenance. Within this region, the influence of Neptune extends far beyond its immediate vicinity, shaping the architecture of distant space through rhythmic gravitational interaction. As part of the broader outer solar system, resonant objects form a critical bridge between stable classical populations and more chaotic distant regions. Their motion reveals how order can emerge from gravitational complexity, creating structured patterns in a region that might otherwise appear sparse and disordered. Beyond the resonant populations of the Kuiper belt, the structure of the outer solar system becomes increasingly diffuse and dynamically disturbed. This region, known as the scattered disk, contains objects whose orbits have been strongly modified by past gravitational encounters, primarily with Neptune. Unlike the stable and rhythmically constrained motion found in resonant zones, these bodies follow paths that are stretched, tilted, and continuously evolving over long timescales. The scattered disk forms a transitional zone between the relatively structured Kuiper belt and the distant, loosely bound population of objects that extend toward the edge of the Sun's gravitational influence. Objects in this region typically have highly elongated orbits, bringing them from relatively distant perihelion points near the outer planetary region to extreme aphelion distances far beyond the main Kuiper belt. This extreme variation in distance reflects a history of gravitational scattering events that altered their original trajectories. The origin of scattered disk objects is closely tied to interactions with Neptune during the early and ongoing evolution of the solar system. When icy bodies from the outer disk passed near Neptune, gravitational encounters could dramatically change their orbital energy. Some were pushed outward into distant orbits, while others were scattered inward or ejected entirely from the solar system. The scattered disk represents the population that remained gravitationally bound but dynamically transformed. The orbits within this region are not stable in the same sense as those in the classical or resonant Kuiper belt. Instead, they evolve over time through repeated weak interactions with Neptune and in some cases with other giant planets. These interactions do not require direct close encounters. Even distant gravitational tugs repeated over millions of years can gradually reshape orbital paths. As a result, scattered disk objects exhibit a wide range of orbital inclinations and eccentricities. The eccentricity of these orbits, a measure of how elongated they are, is often high. This means that many scattered disk objects spend most of their orbital time far from the Sun, only briefly entering regions closer to the planetary system. During these brief inner passages, their motion is faster due to stronger solar gravity, while at their farthest points their motion slows significantly. This variation creates long, stretched orbital cycles that can span thousands or even tens of thousands of years. Inclination within the scattered disk is also highly variable. Some objects remain close to the plane of the solar system, while others travel on steeply tilted orbits that take them far above or below the general planetary alignment. This wide distribution of orbital angles reflects the chaotic nature of their past interactions, where gravitational forces acted from multiple directions and over extended periods. The scattered disk is not a sharply defined boundary, but rather a gradual extension of the Kuiper belt's dynamical influence. There is no clear dividing line where the Kuiper belt ends and the scattered disk begins. Instead, the transition is defined by increasing orbital instability and decreasing resonance structure. Objects in this region are loosely bound and can be gradually perturbed into different orbital states over time. Some scattered disk objects may eventually evolve into long-period comet sources. As their orbits are altered, they can be redirected toward the inner solar system, where solar heating transforms their icy surfaces into active cometary features. Others may be pushed outward even further, potentially becoming part of distant populations influenced more by galactic tides and passing stars than by the Sun itself. The physical composition of scattered disk objects remains similar to other outer solar system bodies. They are primarily composed of frozen volatiles mixed with rocky material reflecting their origin in the cold outer regions of the protoplanetary disk. However, their surfaces often show signs of more complex evolutionary histories. Repeated variations in solar distance expose them to changing levels of radiation and thermal conditions leading to heterogeneous surface features. Because of their distant and faint nature, scattered disk objects are difficult to observe directly. Most are detected only when they approach closer to the Sun during parts of their elongated orbits. This observational limitation means that the known population likely represents only a fraction of the total number of such objects. The full extent of the scattered disk remains partially hidden, inferred through dynamical modeling and limited observational data. The scattered disk plays an important role in connecting the structured regions of the Kuiper belt with the distant outer reservoirs of icy bodies. It acts as a dynamic pathway through which material can be redistributed across the outer solar system. This redistribution process continues today, driven by ongoing gravitational interactions that slowly modify orbital paths over time. The long-term evolution of scattered disk objects is inherently uncertain. Some may remain in elongated orbits for billions of years, while others may eventually be ejected from the solar system entirely due to cumulative gravitational perturbations. This ongoing evolution reflects the unstable balance of forces acting in this distant region, where no single structure dominates for extended periods. In the broader context of outer solar system architecture, the scattered disk represents a region of transition movement and continuous change. It bridges the gap between the relatively organized Kuiper belt and the more distant and loosely bound populations that extend toward interstellar space. Its structure is defined not by stability, but by the memory of past gravitational encounters that continue to shape motion across vast timescales. Beyond the scattered disk, the outer solar system extends into a region where objects are only weakly bound to the Sun and exist in extremely distant, slowly evolving orbits. This region is often described as a detached population of trans-Neptunian bodies. Unlike scattered disk objects which are actively shaped by interactions with Neptune, these distant bodies appear largely isolated from the immediate gravitational influence of the known giant planets. Their motion reflects a different kind of dynamical history, one that suggests either past disturbances or subtle long-term forces acting across vast distances. Detached trans-Neptunian objects occupy orbits with perihelion distances far beyond the range where Neptune can exert strong direct gravitational control. This separation means that their closest approaches to the Sun still occur in regions where planetary perturbations are weak. As a result, their orbits are more stable in shape than those of scattered disk objects, even if they are still highly elongated and distant. These bodies spend the vast majority of their orbital periods in the cold outer reaches of the solar system, far beyond the influence of the main planetary region. The existence of these detached orbits presents an important question in outer solar system dynamics. Standard gravitational interactions with the known planets cannot easily account for how these objects acquired such distant and isolated trajectories. Their current orbital configurations suggest that they were either displaced in the past under different conditions, or influenced by mechanisms that operate at much larger scales than typical planetary encounters. This makes the detached population a key area of interest in understanding the full structure of the outer solar system. The orbits of detached objects are generally highly eccentric, meaning they are stretched into long ellipses around the Sun. However, unlike scattered disk bodies, their closest orbital points remain far from Neptune's effective reach. This separation creates a dynamical decoupling from the main planetary system. Once placed into such distant orbits, these objects experience only weak perturbations over long time scales, allowing their trajectories to remain relatively unchanged compared to more dynamically active populations. Inclination within the detached population varies widely. Some objects move close to the general plane of the solar system, while others travel on steeply inclined paths that take them far above or below it. This diversity in orbital tilt suggests a complex history of dynamical shaping, possibly involving early solar system conditions or external gravitational influences. The distribution does not follow a simple pattern, reflecting the incomplete understanding of how these objects were originally placed into their current orbits. The physical nature of detached trans-Neptunian objects is similar to other distant icy bodies. They're composed primarily of frozen volatiles, such as water ice, methane, and nitrogen compounds, combined with rocky material from the early solar nebula. Their surfaces are subject to long-term exposure to cosmic radiation, which gradually alters their chemical composition. Over time, this radiation processing can darken their surfaces and create complex organic residues that affect their reflectivity. Because of their extreme distances, detached objects are extremely difficult to observe. Most are detected only through long-term sky surveys that track faint, slow-moving points of light. Their vast distances mean they reflect very little sunlight, making them some of the faintest known bodies in the solar system. As a result, the known population is likely incomplete, with many more objects potentially existing beyond current detection limits. The orbital characteristics of detached objects suggest that they are not easily explained by present-day planetary dynamics alone. One possibility is that they were influenced during an earlier epoch when the solar system was more dynamically active. During this period, interactions between migrating giant planets and a denser outer disk of material could have scattered objects into distant detached orbits. Once placed far enough away, these bodies would have become decoupled from further strong planetary influence. Another important aspect of the detached region is its role as a transition between the known solar system and more distant populations that may extend toward the inner boundary of the Oort cloud. While still gravitationally bound to the Sun, detached objects occupy a space where the Sun's influence is significantly weakened compared to inner regions. This makes them sensitive to extremely small perturbations over very long timescales, including those from passing stars or the gravitational field of the Milky Way. The long-term stability of detached orbits depends on a delicate balance of forces. Although they are relatively isolated from Neptune and other planets, they are not completely free from external influence. Over millions to billions of years, small gravitational disturbances can gradually modify their orbital parameters. However, these changes occur so slowly that detached objects appear effectively stable within observational timescales. The presence of this population adds another layer of structure to the outer solar system. It suggests that the transition from the Kuiper belt to interstellar space is not abrupt, but instead composed of multiple overlapping dynamical regions. Each region reflects a different balance of gravitational influence, ranging from strong planetary control to weak solar binding, and eventually to galactic scale effects. The detached population therefore represents a key piece of the outer solar system's architecture. It preserves evidence of past dynamical processes, while also existing in a current state of long-term stability under weak gravitational influence. Its study helps bridge the gap between well-understood planetary dynamics and the more uncertain physics governing the most distant bound objects in the solar system. In the extreme outer reaches of the solar system, where detached trans-Neptunian objects drift in vast and distant orbits, subtle patterns begin to emerge when their orbital properties are examined together. These patterns are not immediately obvious when considering individual objects, but they become more significant when large populations are analysed statistically. Among these distant bodies, certain orbital alignments appear more frequently than random distribution would suggest, creating what is often described as orbital clustering anomalies. These anomalies refer to the tendency of several distant objects to share similar orbital orientations, particularly in the alignment of their elongated paths around the Sun. Instead of being randomly distributed in all directions, a subset of these orbits appears to point in roughly the same region of space. This alignment is not perfect or uniform, but it is persistent enough across multiple observations to draw scientific attention. The effect is most noticeable among the most distant and least gravitationally disturbed objects, where long-term stability allows orbital features to remain preserved. The significance of these clustering patterns lies in the fact that gravitational interactions with known planets, especially Neptune, should tend to randomize orbital orientations over very long timescales. In regions where planetary influence is weak, orbits are expected to become more evenly distributed. The presence of alignment suggests that either an unknown organizing influence is acting on these distant objects, or that observational limitations may be shaping the perceived pattern. One interpretation of these alignments involves the possibility of a distant massive object exerting a subtle but persistent gravitational influence. In this scenario, the clustering would arise from long-term orbital shaping, where repeated weak interactions gradually align the orbits of distant bodies into a preferred orientation. Such a mechanism would not require direct close encounters, but would operate through slow, cumulative gravitational effects over billions of years. However, the observed clustering must also be examined in the context of observational bias. The detection of distant objects depends heavily on where telescopes survey the sky, how sensitive those instruments are, and which regions of space are more frequently observed. If observations are unevenly distributed across the sky, then the detected population may appear artificially clustered, even if the true distribution is more uniform. This possibility makes it necessary to carefully evaluate survey coverage when interpreting the data. Despite these uncertainties, the clustering signal persists in multiple independent datasets, particularly among objects with highly elongated orbits and extreme distances from the Sun. These are precisely the objects least affected by known planetary perturbations, making their orbital orientations especially valuable for understanding long-term dynamical processes. The consistency of the pattern across different observational campaigns strengthens its relevance even if its origin remains unresolved. The mathematical analysis of these orbits involves examining parameters such as the orientation of the orbital ellipse in three-dimensional space. This includes the direction in which the closest and farthest points of the orbit point relative to the Sun and the plane of the solar system. When plotted collectively, these orientations show a tendency toward grouping rather than random scattering, forming a statistical structure that stands out against expected distributions. The physical interpretation of such clustering requires careful consideration of all known gravitational influences. The giant planets, particularly Neptune, have strong effects on objects within and near the Kuiper belt, but their influence weakens significantly at the extreme distances where these clustered objects reside. This weakening of known forces opens the possibility that additional factors, whether gravitational or observational, may be contributing to the observed structure. If a distant massive body were present, its gravitational influence would be extremely subtle at any given moment, but it could accumulate over long timescales. Even a weak but consistent force can gradually reshape orbital orientations if applied continuously across billions of years. This process would not produce immediate or dramatic changes, but would instead create slow, persistent alignment patterns similar to those observed. Alternatively, the clustering may reflect remnants of the early solar system's formation environment. During the period when planets were still forming and migrating, the outer disk of material was dynamically active with frequent gravitational interactions and redistribution of objects. It is possible that some of these primordial structures were never fully erased and have persisted as fossilized orbital patterns preserved in the most distant regions. The challenge in interpreting these anomalies lies in the limited number of observed objects. The extreme distances and faintness of these bodies mean that only a small sample has been detected so far. As a result, statistical uncertainty remains significant, and future observations could either strengthen or weaken the apparent clustering signal. This makes continued deep sky surveys essential for refining the understanding of outer solar system structure. Regardless of its origin, the presence of orbital clustering among distant trans-Neptunian objects highlights the fact that the outer solar system is not entirely random in its architecture. Even in regions where gravitational influences are weak and space appears almost empty, subtle patterns can emerge that reflect either underlying physical forces or the limits of current observation. The study of these anomalies represents a transition point in the exploration of the outer solar system, moving from well-characterized dynamical regions into areas where interpretation becomes more dependent on statistical analysis and incomplete data. Within this uncertain but structured environment, the possibility of additional unseen influences remains an open question in understanding the full architecture of the solar system's outermost regions. As patterns of orbital clustering persist among the most distant known trans-Neptunian objects, scientific interpretation begins to consider whether a hidden massive influence could exist far beyond Neptune. This idea emerges not as a direct observation, but as a theoretical response to repeated statistical structure in orbital orientations. In this context, a distant unseen planet becomes one possible explanation for why certain extreme orbits appear aligned rather than randomly distributed. The hypothesis proposes that a large planetary mass object may exist on a distant elongated orbit around the Sun far beyond the reach of current direct detection. Such an object would not be part of the classical planetary system and would remain extremely difficult to observe due to its distance and low reflected sunlight. Its presence would only be inferred indirectly through its gravitational effects on smaller bodies in the outer solar system. In this framework, the gravitational influence of a distant planet would act over extremely long timescales, subtly shaping the orbits of detached trans-Neptunian objects. Rather than causing immediate disruptions, its effect would accumulate, gradually gently organizing orbital orientations into preferred directions. This process would be slow and continuous, operating over billions of years, consistent with the timescales involved in outer solar system evolution. The idea of such a planet arises specifically from the need to explain why clustering appears stronger than expected from known gravitational sources alone. Neptune, while dominant in the outer planetary region, loses much of its influence at extreme distances. Beyond this range, orbital dynamics should become increasingly random if no additional forces are present. The persistence of structure at these distances motivates consideration of alternative gravitational shaping mechanisms. A distant planet could, in theory, maintain a stable orbit if it resides far enough from the Sun to avoid strong perturbations from the known giant planets. Such an orbit would likely be highly elongated, carrying the object through regions of space where its influence on other bodies varies significantly depending on its position along its path. When closer to the inner solar system, its gravitational effects would be stronger, while at farthest distances its influence would weaken substantially. The interactions between such a hypothetical planet and smaller trans-Neptunian objects would not involve direct collisions or close encounters in most cases. Instead, the influence would occur through repeated weak gravitational tugs that alter orbital orientation over long periods. These cumulative effects could produce the observed clustering patterns if the configuration and mass of the distant object are appropriate. Numerical models are used to test whether such a planet could reproduce the observed orbital structures. These simulations involve placing a large unseen object in different hypothetical orbits and tracking how it influences population of distant small bodies over time. The results depend strongly on assumptions about mass distance, orbital inclination, and eccentricity. Some configurations produce clustering patterns similar to those observed, while others do not. At the same time, the hypothesis remains constrained by the absence of direct observational evidence. Despite extensive sky surveys, no large distant planet has been directly detected in the regions predicted by some models. This lack of detection places limits on the possible size, brightness, and distance of any such object. If it exists, it must be faint enough and distant enough to have escaped current detection capabilities. The search for a distant planet is also influenced by the limitations of observational coverage. Large portions of the sky are surveyed at different depths and times, and faint moving objects can be difficult to distinguish from background stars and galaxies. As a result, even if a massive distant object were present, detecting it would require careful long-term observation across wide regions of the sky. The hypothesis does not stand alone, but is evaluated alongside alternative explanations. Some models suggest that the observed clustering could arise from observational bias, where the regions of sky most frequently surveyed happen to align with certain orbital orientations. Other models propose that collective gravitational interactions among smaller objects could produce weak alignment effects without requiring a single dominant unseen body. Despite these alternatives, the idea of a distant planet remains a useful framework for exploring how strong gravitational structures could exist in the outer solar system without being directly visible. It provides a testable mechanism that can be refined or rejected as new observational data becomes available. The strength of the hypothesis lies in its ability to connect statistical orbital patterns with physical gravitational processes. If such a planet exists, it would represent a significant extension of the known solar system architecture. Its presence would imply that the outer solar system is more dynamically complex than previously understood, with large-scale structures extending far beyond the classical planetary boundaries. It would also reshape understanding of how planetary systems evolve and retain distant massive bodies over long timescales. The current scientific status of the hypothesis remains open. It exists at the intersection of observation, statistical analysis, and dynamical modeling. As more distant objects are discovered and catalogued, the statistical significance of orbital clustering will become clearer, allowing stronger constraints to be placed on any potential hidden influence. Within the broader context of outer solar system exploration, the idea of a hidden planet represents a transition from direct observation to inference. It reflects how subtle patterns in motion can suggest the presence of unseen structures, even in regions where direct detection remains challenging. Whether confirmed or disproven in the future, the hypothesis plays a central role in shaping current understanding of distant solar system dynamics. As the hypothesis of a distant massive object continues to be evaluated, attention turns to how gravitational modeling can reproduce the observed behavior of distant trans-Neptunian objects. In this approach, The outer solar system is treated as a long-term dynamical system, where the motion of many small bodies is simulated under the influence of known planets and potential additional forces. The goal is to determine whether a single unseen influence can naturally generate the orbital patterns that appear in observational data. These models begin by representing the known giant planets, particularly Neptune, Uranus, Saturn, and Jupiter, as the dominant sources of gravitational structure in the solar system. Their masses, positions, and orbital motions are well constrained, allowing simulations to accurately reproduce their influence on smaller objects. Within this framework, the outer disk of icy bodies is populated with test particles that represent trans-Neptunian objects. Their motion is then tracked over extremely long timescales to observe how their orbits evolve. When only known planets are included, simulations show that distant objects tend to become widely dispersed over time. Neptune, while influential in shaping the Kuiper belt and scattered disk, is not sufficient on its own to produce the strongest observed clustering in the most distant orbits. Instead, orbital orientations gradually spread, leading to a more random distribution than what is currently observed among extreme trans-Neptunian populations. To test alternative scenarios, models introduce an additional massive object on a distant elongated orbit. This hypothetical body is placed in various positions with different values for orbital distance, inclination, and eccentricity. The gravitational influence of this object is then allowed to interact with the simulated population of small bodies over billions of years. The resulting orbital distributions are compared with observational data to evaluate how closely they match. In simulations where the additional object has sufficient mass and resides on a distant inclined orbit, the resulting system can produce regions of orbital alignment similar to those observed. The mechanism behind this effect is the gradual reshaping of orbital orientations through repeated weak gravitational interactions. Over long timescales, these interactions can confine the directions of elongated orbits into preferred regions of space. The strength of this effect depends heavily on the specific parameters chosen for the hypothetical object. A more massive object produces stronger alignment, but is also more likely to have been detected already through its gravitational influence on known planets or through direct observation. A less massive object produces weaker alignment, which may not fully explain the observed clustering. This balance creates a narrow range of possible configurations that remain consistent with both dynamical models and observational limits. Orbital inclination of the hypothetical object also plays a critical role in the simulations. If the orbit is significantly tilted relative to the main planetary plane, it can induce corresponding tilts in the orbits of distant small bodies. This can help explain why some extreme trans-Neptunian objects exhibit unusually high inclinations that are difficult to account for through interactions with known planets alone. The simulations also show that the timing of gravitational interactions is important. As the hypothetical object moves along its elongated orbit, its influence on distant bodies varies depending on its position. When it's closer to the inner solar system, its gravitational reach is stronger and can more effectively reshape orbital structures. When it moves far away, its influence weakens, allowing previously shaped structures to persist without immediate disruption. Despite the success of some models in reproducing certain features of the observed data, no single configuration fully explains all aspects of the outer solar system structure. Some simulations produce clustering but fail to match the full range of orbital inclinations. Others match inclinations but overpredict the number of unstable or ejected objects. This indicates that the system is sensitive to initial conditions and that multiple processes may be contributing simultaneously. Computational limitations also play a role in interpreting these results. Simulating the evolution of thousands of objects over billions of years requires simplifying assumptions and numerical approximations. Small differences in initial conditions can lead to divergent outcomes over long timescales, making it difficult to determine whether a particular model reflects physical reality or numerical artifact. Even with these uncertainties, gravitational modeling remains one of the most powerful tools for exploring the outer solar system. It allows scientists to test whether observed structures can arise naturally from known physics, or whether additional influences are required. The results consistently show that known planets alone struggle to fully account for the most distant orbital patterns. As a result, the possibility of an unseen influence remains present within the modeling framework, not as a confirmed object, but as a testable parameter. Its inclusion helps explore the range of possible dynamical histories that could lead to the current configuration of distant bodies. In this sense, the models serve as both a reconstruction of past evolution and a probe of potential unseen structure. The broader implication of these simulations is that the outer solar system may be shaped by subtle, long-term gravitational effects that are not immediately visible, but accumulate over vast timescales. Whether these effects originate from a single distant object or from a combination of smaller influences remains an open question within current scientific understanding. As gravitational models continue to explore the structure of the outer solar system, a critical step involves isolating the known influences of the giant planets to determine whether they alone can account for observed orbital behavior. In this context, the roles of Jupiter, Saturn, Uranus, and Neptune are examined in detail, since these bodies dominate the gravitational architecture of the solar system beyond the asteroid belt. Jupiter exerts the strongest gravitational force among the planets, but its influence is most significant in the inner and mid-regions of the solar system. At the vast distances of trans-Neptunian space, its direct perturbations become extremely weak. However, over long timescales, Jupiter can still contribute to slow changes in the energy distribution of small bodies, particularly those that migrate inward from distant regions. Its role is therefore indirect but not entirely negligible in shaping long-term dynamical evolution. Saturn, while less massive than Jupiter, contributes to complex gravitational resonances that can influence the motion of objects that cross its orbital region. In the context of the outer solar system, its role is primarily connected to the intermediate pathways of objects that move between the scattered disk and inner planetary regions. Its long-term influence is cumulative, but it does not strongly shape the most distant orbital structures. Uranus occupies a more direct position in the architecture of the outer solar system. Its gravitational field interacts more closely with trans-Neptunian populations, particularly those in transitional orbits. Uranus contributes to subtle orbital diffusion, helping redistribute objects over long periods. However, like the other giant planets, its ability to produce coherent, large-scale alignment patterns at extreme distances is limited. Neptune is the most significant planetary influence in the outer solar system beyond Uranus. It plays a central role in shaping the Kuiper Belt resonant populations and scattered disk. Its migration during the early solar system is believed to have strongly reorganized the distribution of icy bodies, capturing objects into resonances and scattering others into distant orbits. Even today, Neptune continues to act as a primary source of dynamical structure in nearby trans-Neptunian space. Despite this strong influence, Neptune's gravitational reach weakens significantly at the distances where detached objects and extreme trans-Neptunian bodies reside. Beyond a certain threshold, its ability to directly control orbital orientation diminishes, and its perturbations become increasingly diffuse. In these distant regions, Neptune's influence is no longer sufficient to impose strong directional alignment across multiple objects. When models include only the known giant planets, the resulting orbital distributions tend to lack the level of coherence observed among the most distant bodies. Instead of forming aligned clusters, orbits gradually disperse into broader, more randomized distributions over time. This outcome suggests that while the giant planets are responsible for much of the structure in the outer solar system, they may not fully account for the most extreme orbital patterns. The inability of known planets to reproduce certain clustering features does not imply a failure of gravitational theory, but rather highlights the limitations of known mass distribution in the outer solar system. Gravity behaves consistently according to established laws, but the resulting structures depend entirely on the distribution of mass and the initial conditions of the system. If additional mass exists at extreme distances, even in relatively small amounts, it could alter long-term orbital evolution in measurable ways. The search for alternative explanations includes considering whether collective effects among many small bodies could contribute to observed structures. In such scenarios, the combined gravitational influence of numerous distant objects might produce weak alignment over long timescales. However, simulations generally indicate that the total mass of known trans-Neptunian populations is insufficient to generate strong persistent clustering effects of the kind observed. Another factor examined in these models is the historical evolution of planetary orbits. The giant planets are not believed to have formed in their current positions. Instead, they likely migrated during the early stages of solar system formation, reshaping the distribution of smaller bodies as they moved. While this migration explains many features of the Kuiper belt and scattered disk, it does not fully account for alignment in the most distant orbital populations. The comparison between known planetary influences and observed orbital patterns highlights a gap in explanatory power at extreme distances. This gap does not point to a specific solution, but indicates that additional processes or structures may be required to fully describe the system. These could include previously unrecognized gravitational sources or long-term dynamical effects that have not yet been fully modeled. Within this framework, the known planets define a strong but incomplete gravitational backbone for the outer solar system. They establish the primary structure of the Kuiper belt and influence the scattered disk, but their reach fades as distance increases. Beyond this range, orbital behavior becomes increasingly sensitive to weaker forces and subtle perturbations. The study of these limitations is essential for understanding the full architecture of the solar system. It reveals not only what is known, but also where current models reach the boundaries of their explanatory scope. In these outermost regions, the interplay between known planetary forces and potential additional influences remains an active area of investigation. At the outer limits of the solar system, understanding orbital structure depends not only on gravitational dynamics, but also on the limits of observation itself. The ability to detect distant objects is constrained by faint light, vast distances, and the slow motion of bodies across the sky. These constraints shape what is known about trans-Neptunian populations and influence how orbital patterns are interpreted. Most distant objects are detected through reflected sunlight. At extreme distances, sunlight is extremely weak, and the amount of light reflected back toward Earth becomes minimal. This means that only objects with sufficient size or reflective surfaces can be observed directly. Smaller bodies, even if numerous, remain below detection thresholds. As a result, the observed population represents only a fraction of the true distribution in the outer solar system. The motion of these objects across the sky is also extremely slow. Because they are so far from the Sun, their orbital speeds are low, and their apparent movement against background stars is gradual. Detecting such motion requires repeated observations over long periods of time. Without extended tracking, distant objects can easily blend into static background fields, making them difficult to distinguish from distant stars or galaxies. Survey coverage plays a significant role in shaping the known population. Telescopes do not observe the entire sky uniformly. Instead, observations are concentrated in specific regions based on instrument availability, observational goals, and environmental conditions. This uneven coverage introduces biases in the detected distribution of distant objects. Certain regions of the sky may be more thoroughly surveyed, increasing the likelihood of detecting objects in those directions. These observational biases can influence the apparent orbital structure of trans-Neptunian populations. If surveys preferentially detect objects in certain parts of the sky, the resulting dataset may show artificial clustering. This does not mean the clustering is necessarily absent in reality, but it does mean that careful statistical correction is required to separate genuine physical structure from observational effects. Detection limits also vary depending on the brightness of objects and the sensitivity of instruments. Modern wide-field surveys can detect increasingly faint objects, but there remains a threshold below which objects are effectively invisible. This means that the smallest and most distant bodies remain largely unobserved, leaving gaps in the known population. These gaps must be accounted for when interpreting orbital distributions. The challenge of incomplete data is especially significant in the region beyond Neptune, where orbital periods can span thousands or even tens of thousands of years. Because observations only cover a small fraction of these long cycles, orbital parameters must often be inferred from limited segments of motion. This introduces additional uncertainty into estimates of orbital shape, inclination, and orientation. To address these limitations, long-term sky surveys are conducted using wide-field telescopes that repeatedly scan large portions of the sky. These surveys accumulate data over years or decades, gradually building a more complete picture of distant solar system populations. Each new detection adds to the statistical sample, refining estimates of orbital distribution and reducing uncertainty in clustering analysis. Despite these efforts, the known population remains incomplete. Many distant objects likely exist beyond current detection capabilities, particularly those that are small, dark, or located in regions of the sky that have not been extensively surveyed. This incomplete sampling must be considered when interpreting any apparent large-scale structure in orbital data. The relationship between observational limits and theoretical interpretation is therefore tightly linked. Patterns observed in the data may reflect true physical structures, observational biases, or a combination of both. Distinguishing between these possibilities requires careful modeling of survey sensitivity and sky coverage. In some cases, apparent clustering of orbital elements may weaken when observational biases are accounted for. In other cases, the patterns remain statistically significant even after corrections. This ongoing refinement of data analysis plays a central role in determining whether observed structures are physically meaningful or artifacts of detection methods. The extreme distance of these objects also introduces delays in confirmation. Because orbital motion is so slow, verifying the full path of an object can take many years of observation. During this time, estimates of orbital parameters may change as additional data becomes available. This gradual refinement process is essential for building accurate models of the outer solar system. As observational techniques improve, the ability to detect smaller and more distant objects continues to increase. New instruments and survey methods expand the range of detectable bodies, gradually filling in gaps in the known population. However, even with these advances, the outer solar system remains only partially mapped. This incomplete view means that any interpretation of large-scale orbital structure must remain cautious. Observed patterns provide valuable clues, but they exist within the constraints of what can currently be detected. The true distribution of objects may be broader and more complex than present data suggests. In this context, the outer solar system is not only a physical region, but also an observational frontier. The limits of detection define the limits of knowledge, and each improvement in survey capability reshapes the understanding of distant space. The interplay between observation and interpretation remains a central factor in studying the most remote regions of the solar system. Beyond the limits of visible light surveys, the exploration of the outer solar system extends into wavelengths that reveal colder and more distant objects. Infrared observations become especially important in this context because distant bodies that reflect very little sunlight can still emit faint thermal radiation. This radiation arises from residual heat absorbed over long periods even at extreme distances from the Sun. Infrared sky surveys operate by detecting this weak thermal emission, allowing astronomers to identify objects that are otherwise invisible in optical light. In the cold outer solar system, temperatures are extremely low, but not absolute zero. Even minimal thermal energy is enough for large distant objects to emit detectable infrared signals. This makes infrared instruments essential for extending the observable range of trans-Neptunian space. Wide-field infrared surveys scan large portions of the sky, systematically building maps of faint heat sources. These surveys complement optical observations by revealing objects that do not reflect enough sunlight to be seen directly. In some cases, infrared detection can confirm the presence of distant bodies that were only weakly indicated in optical data, improving the completeness of orbital catalogues. However, infrared detection also faces limitations. The sensitivity of instruments decreases with distance and object size, meaning that only relatively large or moderately warm distant bodies can be observed. Very small or extremely cold objects remain below detection thresholds. In addition, background infrared radiation from interstellar dust in the Milky Way itself can interfere with faint signals, complicating the identification process. The combination of optical and infrared data provides a more complete view of the outer solar system than either method alone. Optical surveys are more sensitive to reflected sunlight and can track motion over time, while infrared surveys are more sensitive to thermal emission and can reveal hidden populations. Together, they help reduce observational bias and improve estimates of the total population of distant objects. In addition to infrared methods, other wide-field sky surveys contribute to the search for faint outer solar system bodies. These surveys repeatedly image large areas of the sky over long periods, allowing for the detection of slow-moving objects through changes in position. By comparing images taken at different times, astronomers can identify subtle motion that distinguishes distant solar system objects from background stars. The combination of time-domain observation and multi-wavelength analysis is essential for building a reliable census of trans-Neptunian space. Each method contributes different types of information, and together they reduce the uncertainty inherent in studying such distant and faint populations. Despite this progress, the outermost regions remain only partially surveyed. Survey depth, or the ability to detect faint objects, is a key factor in determining how much of the outer solar system can be mapped. Deeper surveys can identify smaller and more distant bodies, but require longer exposure times and more sensitive instruments. These requirements limit the speed at which full sky coverage can be achieved. Another important factor is sky motion rate. Objects in the outer solar system move so slowly that their motion over short observation periods may be nearly imperceptible. This requires specialized data analysis techniques to distinguish genuine motion from background noise. Long-term tracking is essential for confirming that a faint object is truly part of the solar system rather than a distant background source. Infrared surveys also contribute to understanding the physical properties of distant objects. Thermal emission depends not only on size and distance, but also on surface composition and reflectivity. By comparing infrared brightness with optical brightness, it is possible to estimate properties such as albedo, or surface reflectivity. These estimates help characterize the composition of trans-Neptunian populations more accurately. The integration of infrared and optical data has led to the discovery of several previously unknown distant objects. Each new detection helps refine models of orbital distribution and improve statistical analyses of outer solar system structure. However, even with these advancements, the total number of known objects remains small compared to the likely true population. The limitations of current surveys mean that many distant bodies may still be undiscovered. These undetected objects could include smaller trans-Neptunian bodies, or larger, more distant objects that remain too faint for current instruments. This uncertainty directly affects interpretations of orbital clustering and large-scale structure. As observational technology continues to improve, future surveys are expected to extend the detection range further into the outer solar system. Larger telescopes, more sensitive detectors, and longer observation baselines will gradually reduce current gaps in coverage. Each improvement brings a clearer picture of the distant regions where solar influence fades and interstellar space begins to dominate. In this way, infrared sky searches and wide-field surveys work together to expand the known boundaries of the solar system. They reveal not only individual objects but also the broader structure of distant space, gradually transforming unknown regions into mapped and studied environments. Despite these advances, the farthest reaches remain only partially revealed, preserving uncertainty about the full extent of trans-Neptunian populations. To understand the long-term evolution of distant trans-Neptunian populations, scientists rely heavily on numerical simulations that reconstruct orbital motion across billions of years. These simulations are designed to replicate the gravitational environment of the outer solar system by combining the known masses and positions of the Sun and giant planets with a large number of small test objects representing icy bodies in distant space. Each simulated object follows the same fundamental laws of motion governed by gravity, but the system as a whole evolves in complex ways due to repeated interactions. Over long timescales, even weak gravitational forces can accumulate into significant changes in orbital shape and orientation. This sensitivity makes the outer solar system a dynamically rich environment, where small differences in initial conditions can lead to widely different outcomes. The process begins by assigning initial orbital parameters to thousands or even millions of simulated objects. These parameters are chosen to represent plausible conditions in the early solar system, often based on models of the protoplanetary disk. The objects are then allowed to evolve under the gravitational influence of the Sun and planets, with their trajectories calculated step by step over extended periods of simulated time. As the simulation progresses, objects experience a variety of gravitational effects. Some are gradually scattered outward by interactions with Neptune, while others become trapped in resonant configurations or settle into stable orbits. A fraction may be ejected entirely from the system after repeated perturbations. This range of outcomes reflects the diversity of dynamical pathways available in the outer solar system. One of the key strengths of numerical simulation is the ability to test different hypothetical configurations. By adjusting initial conditions or introducing additional massive objects, researchers can observe how the system responds over time. This allows for direct comparison between simulated orbital distributions and observed data from telescopic surveys. When only known planets are included, simulations tend to produce a broad dispersion of orbital orientations over long timescales. This result is consistent with expectations of gravitational diffusion, where repeated weak interactions gradually randomize orbital alignment. However, this outcome does not always fully match the structured clustering seen in the most distant observed objects. To explore alternative scenarios, simulations introduce additional variables such as distant massive perturbers or variations in early solar system conditions. These modifications can significantly alter the resulting orbital architecture. In some cases, they produce regions of alignment and clustering that resemble observed patterns, suggesting that additional influences may be capable of shaping the outer solar system in subtle but measurable ways. The accuracy of these simulations depends on computational precision and the treatment of long-term numerical stability. Small numerical errors can accumulate over millions of simulated years, potentially affecting final results. To reduce this uncertainty, high-precision integrators are used, and simulations are often repeated multiple times with slightly varied initial conditions to test consistency. Another important factor is the chaotic nature of gravitational systems. In regions where orbital interactions are particularly sensitive, small differences in starting conditions can lead to diverging outcomes. This chaos does not imply randomness, but rather reflects the inherent complexity of multi-body gravitational systems over long timescales. Despite these challenges, numerical modeling remains one of the most powerful tools for studying regions of the solar system that cannot be directly observed in full. It allows scientists to reconstruct possible histories and evaluate whether observed structures can arise naturally under known physical laws, or whether additional influences are required. Simulations also provide insight into the long-term stability of distant objects. Some orbits remain stable over billions of years, while others gradually evolve into more extreme configurations or become unstable. This helps explain why the outer solar system contains both relatively ordered populations and highly dispersed objects. In the context of the potential hidden planet hypothesis, simulations play a central role in testing whether such an object could reproduce observed orbital clustering. By varying its assumed mass, orbit, and inclination, researchers can evaluate a wide range of possible scenarios and compare the resulting structures to actual data. However, no single simulation fully reproduces all observed features of the outer solar system. Some models match clustering but fail to account for the full range of orbital inclinations. Others reproduce inclination distributions but overestimate instability or ejection rates. This indicates that the system likely depends on multiple interacting factors rather than a single dominant influence. Even with these limitations, simulation results consistently show that the outer solar system is sensitive to small gravitational perturbations over long timescales. This sensitivity means that even subtle differences in mass distribution can produce measurable differences in orbital structure when extended across billions of years. As computational power continues to increase, simulations become more detailed and more accurate, allowing for larger populations and longer integration times. This improvement helps refine models of outer solar system evolution and narrows the range of plausible explanations for observed orbital patterns. In this way, numerical simulations serve as a bridge between observation and theory, transforming limited observational data into broader dynamical understanding. They provide a framework for exploring how the outer solar system may have evolved and how unseen influences might still shape its most distant regions. As multiple lines of evidence are examined, the interpretation of distant orbital clustering in the outer solar system becomes increasingly dependent on distinguishing physical structure from observational effects. Competing explanations are evaluated by comparing how well they reproduce the observed distributions, while remaining consistent with known constraints on mass, motion, and detection limits. One class of explanations focuses on observational bias. In this view, the apparent alignment of distant trans-Neptunian orbits may arise from the way surveys are conducted rather than from a true physical structure. Telescopic observations do not cover the sky uniformly, and many surveys concentrate on specific regions where detection is easier or more efficient. If distant objects are preferentially discovered in certain sky directions, the resulting data set may appear artificially clustered even if the true distribution is more uniform. To test this possibility, scientists model the sensitivity and coverage of observational surveys in detail. These models account for pointing direction, exposure, time detection thresholds, and seasonal visibility. When these factors are applied to simulated populations with no intrinsic clustering, some degree of apparent structure can emerge. However, in many cases this induced structure does not fully match the strength or consistency of the clustering observed among the most distant objects. Another class of explanations considers the possibility of collective gravitational effects among many small bodies. In this scenario, the combined influence of a large population of distant objects could over extremely long timescales produce weak alignment without requiring a single dominant unseen planet. Each object contributes a very small gravitational effect, but together they form a diffuse background influence that could slowly modify orbital orientations. However, estimates of the total mass in the outer solar system suggest that this collective influence is likely too weak to generate strong coherent clustering. The mass of known trans-Neptunian populations is small compared to the requirements needed to significantly reshape orbital orientations at extreme distances. As a result, while collective effects exist, they are generally considered insufficient to fully explain the observed patterns on their own. A third category of explanation returns to early solar system conditions. During the formation and migration of the giant planets, the outer disk of material experienced strong dynamical reshaping. Objects were scattered, resonantly captured, and redistributed over large distances. It is possible that some of the observed orbital structure is a fossil remnant of these early processes, preserved in the most distant and least perturbed regions of the solar system. This idea suggests that the current clustering may not require an ongoing influence, but instead reflects ancient dynamical architecture that has survived in a weakened form. However, simulations of early solar system evolution often show that strong initial structures tend to diffuse over time, especially under continued perturbations from the giant planets. This makes it difficult to preserve highly specific alignment patterns over billions of years without some ongoing stabilizing mechanism. A fourth possibility involves combinations of multiple weak effects rather than a single dominant cause. In this framework, observational bias, early solar system remnants, and weak gravitational influences may all contribute simultaneously to the observed structure. Each factor alone may be insufficient, but together they could produce a pattern that resembles clustering when viewed through limited observational data. The challenge with combined explanations is that they often lack predictive specificity. While they can reproduce broad features of the data, they may not generate precise testable predictions about future observations. This makes it difficult to distinguish them from models that include a single dominant perturbing influence. Statistical significance plays a central role in evaluating all these possibilities. The number of known extreme trans-Neptunian objects remains small, which means that statistical fluctuations can have a large impact on perceived structure. As more objects are discovered, the strength and consistency of the clustering signal may increase, decrease, or shift in character. This evolving dataset is critical for determining which explanation best matches reality. The limitations of current observations also mean that confidence levels must be interpreted cautiously. Apparent patterns can strengthen or weaken as new data is added, and early signals may not always persist. This dynamic nature of the dataset requires continuous reassessment of all competing hypotheses. At present, no single explanation fully accounts for all observed features of the outer solar system. Observational bias can influence apparent structure, but does not fully reproduce it in all cases. Collective gravitational effects are present but appear too weak. Early solar system remnants provide partial context but do not consistently maintain alignment over time. Combined models offer flexibility but lack strong predictive constraint. This leaves the interpretation of distant orbital clustering in an intermediate state where multiple possibilities remain open. The data does not yet definitively favor one explanation over others, and further observational evidence is required to reduce uncertainty. In this context, the outer solar system remains a region where theory and observation are still being brought into alignment. The structure seen today may reflect a mixture of long-term dynamical evolution and observational limitations, with the true underlying cause still gradually emerging as new data accumulates. As the study of the outer solar system reaches its most distant and least certain boundary, attention turns to the overall status of current understanding and the limits of what can be confidently concluded. The region beyond Neptune is now known to contain a structured collection of icy bodies ranging from stable classical populations to resonant group scattered objects and detached trans-Neptunian bodies. Each of these populations reflects a different aspect of long-term gravitational evolution, shaped primarily by the giant planets and the early history of the solar system. The classical Kuiper belt provides a relatively stable record of primordial material that has remained in place over billions of years. Resonant populations demonstrate how orbital motion can be organized through repeated gravitational interactions with Neptune. The scattered disk reveals a more chaotic history of orbital disruption and redistribution. Detached objects extend this picture, further occupying distant regions where planetary influence becomes weak and long-term stability depends on subtle dynamical balances. Together, these regions form a layered structure that describes the outer solar system as a continuum rather than a set of isolated zones. Within this framework, the idea of unusual orbital clustering among the most distant objects remains one of the most debated features. Observations suggest that certain extreme orbits may share preferred orientations, but the limited number of known objects and the challenges of detection make it difficult to determine whether this pattern reflects true physical structure or observational influence. The evidence is suggestive but not definitive, and its interpretation continues to evolve as new data becomes available. The hypothesis of a distant unseen planet arises as one possible explanation for this structure. In this scenario, a large faint object on a distant orbit could slowly shape the orientation of extreme trans-Neptunian objects through weak but persistent gravitational interactions. Numerical simulations show that such a mechanism can reproduce some features of the observed clustering under specific conditions, but no configuration has yet accounted for all observed properties simultaneously. Additionally, the absence of direct detection places constraints on the size and distance of any such object, leaving its existence unconfirmed. At the same time, alternative explanations remain viable. Observational bias continues to be a significant factor in shaping the known dataset, as survey coverage is uneven and detection limits restrict the observable population. Early solar system processes may also have left behind subtle remnants of past dynamical structure, preserved in the most distant and least disturbed regions. Combined effects of multiple weak influences remain a possibility, though they are difficult to test with precision. What emerges from all these lines of investigation is a picture of a system that is both structured and incomplete in its current observational form. The outer solar system is governed by well-understood gravitational laws, yet its full architecture is not fully mapped. The known populations provide strong constraints on models, but gaps in detection and statistical uncertainty leave room for multiple interpretations. As observational technology improves, future surveys are expected to significantly expand the catalogue of distant objects. Larger telescopes, deeper sky coverage, and longer time baselines will gradually reduce uncertainty in orbital measurements and improve statistical confidence in clustering analyses. Each new discovery has the potential to either strengthen or weaken current hypotheses, refining the understanding of how the outer solar system is organized. In this evolving context, the current scientific status remains open but increasingly constrained. The outer solar system is no longer viewed as a random collection of distant bodies, but as a dynamically shaped environment with distinct structural regions. However, the cause of certain extreme orbital patterns remains unresolved, and whether they arise from unseen mass-subtle biases or long-term dynamical history is still under active investigation. The exploration of this distant region therefore represents a transition in planetary science from direct structural mapping to interpretation under uncertainty. It highlights how much of the solar system's architecture can be inferred indirectly, even when direct observation is limited. As data improves, the balance between competing explanations will continue to shift, gradually narrowing the range of possible models. In the end, the outer solar system stands as a partially revealed boundary of the known planetary system, where structure, uncertainty, and discovery coexist. Its distant objects preserve evidence of ancient processes, ongoing gravitational interactions, and observational limits, all layered together into a single evolving picture. The question of whether a hidden planet exists remains open, not as a conclusion, but as a carefully constrained possibility within a much larger and still unfolding system.